So I hire that person only if they're better than what I have so far. So the question is, why would I want to hire the last person?
Because you already find the last but one person.
So why was, so I'm not sure if you're answering the way I'm expecting you to answer. So why would I hire the last person?
You only conduct the interview if the position is empty.
Well, it's never empty. Because right now, the person I have right now, which is nobody, is infinitely bad. They're infinitely bad. So that means the first person I interview will be better than infinitely bad. So I will always hire the first person. But why would I hire the last person? Well, they will. I only will hire the last person if they're better than the person I currently have. But before I interview the last person, who is the person that I currently have? Right. We're still working on this logic here. Okay. Okay, so let's say the cost to interview a person is CI. CI is the cost of interviewing. And the cost of hiring is CH. Okay? So the rules are I have to have somebody hired at all times, and that will be the best candidate seen so far. So whenever we interview a candidate who is better than the current person, we fire the current person, and we hire the new candidate. Since I need to have someone hired at all times, we will always hire the first person because they're better than infinitely bad. So what is the cost of the strategy? So here's the algorithm. So we'll assume that the person's quality is some number which is more than 0. So we'll put 0 into the best, and then we'll interview the person's I from 1 to n, the n candidates. We'll interview candidate I. If candidate I is better than a candidate best, then the best gets I, and we'll hire a candidate I. That's the algorithm, pretty simple. So the cost of hiring the best candidate could occur if n candidates are interviewed, because that's all of them, and we hire m of them, where m is less than or equal to n. We have to pay NCI for the interviews of n candidates. It doesn't matter how many we hire, we have to interview them all. That's our model. So the only cost that we can lower in this theta is NCH. Because n is fixed. But m is variable, because it's just a number that's less than or equal to n. So we'll focus on analyzing the hiring cost, MCH, which is this one right here. MCH varies with each permutation. Now, what do I mean by permutation? Well, again, imagine that we are going to be interviewing n people. So the people are 1 through n, right? Now, we don't know how good the first person is. Maybe they're right in the middle. Maybe they're the worst, maybe they're the best. I have no idea. The first person is the first person. The quality of them is unknown. We don't know how good they are. So, when the first person comes in, I will hire them because I have nobody. But when the second person comes in, I will only hire them if they're better than the first person. If they're not, I'm going to wait for the next day, and then the third person will come in. I'll hire them if they're better than the first person. If they're not, no, fourth person comes in the next day. If they're better than the first person, then I don't fire them, and I'll hire person number 4. So there are 2 orders that are important here. One is the order of the candidates. If we have n candidates, then the number of orders they can be put in is n factorial. If we have n candidates coming, number of orders that can be put into is n factorial. That's pretty common, right? Pretty straightforward. Now, so let's talk about in the sequence. So we can say, for example, P sub 1, P sub 2, P sub 3, P sub 4, that's person sub I. Person sub 4, for example, what's their quality? Well, that's going to be the quality, and the quality is not 4. Just because you're first to be interviewed doesn't mean you're the best. Just because you're last interviewed doesn't mean you're... So the sequence is uncorrelated and is independent of the quality. So everybody agrees that the number of orders we can have n candidates come in to get interviewed is n factorial. Okay. So for example, if I have 5, then number of orders is what? 120. 5 times 4 times 3 times 2. 5 factorial. Now the worst case analysis is that m actually equals to n. The worst case analysis is where we hire all candidates, so m is equal to n. How could that happen? How could we hire every single candidate? Every candidate has to be better than the previous one. So, let's suppose we have 10 candidates. How many permutations of 10 candidates do we have roughly? About 3.6 million. So 10 permutations, 10 factorial is about 3.6 million. So that's how many orders we can put 10 people in. How many of those orders would trigger the worst case? Only one. So let's think about the quality. We have 10 people, they have a sequence order, but they also have a quality. To make things more clear and also more confusing, let's suppose that their quality is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means they're increasing in quality. So person 1 has quality 1. Person 2 has quality 2. Coincidentally, person 3 is quality 3. So the only way I'm going to hire everyone is that the worst person has to be hired as the first position. And I cannot, and the second person must have quality 2. Because if they had quality 3, which is better than 1 or 2, and they were second, then when the person with quality 2 came up, I wouldn't hire them. So in order to hire everyone, which is the worst case, because that maximizes the hiring cost, I would have to have the order be in ascending order, from lowest quality 1 up to top quality 10. From lowest quality 1 to top quality n. Okay? So that's the worst case. So the worst case occurs if each candidate is better than the candidates come in increasing order. So at that point, we have cost is theta or O NCI plus NCH, which is O NCH. Of course, if that's the only question I have to ask, everybody can get that correctly very easily. It's very simple cost. What do we expect in an average case? This is where probability comes in. Whenever you hear that word average, it's like, huh, okay, what is it gonna do this time? So average case. Well, I guess average case means a typical case. What do I expect? Imagine a real scenario. I own an agency. I will have a candidate sent in for the first 10 days of this week and next week. So I'll get 10 candidates, Monday, Tuesday, Wednesday, Thursday, Friday, and then Monday through Friday next week. And I want to make sure that I'm trying to get the best person. They may know who's the best person, but they may not be the best person for me. So I'm going to ask them to send them in random order. And if they can't do that, because sometimes they might send you like a couple of bad people and a really good person to make the good person look even better than they actually are, I could say, send me the names of the 10 people that you would like to send to us. And then we'll randomize the names and we'll ask you who to send. And that will ensure that the people are coming in random order. And if they're coming in random order, then I can say, I wonder how many people I'm actually going to hire. So randomizing the sequence. Randomizing the sequence means that every person is equally likely to occur at any position. If I have 10 people, what's the probability that the best person is the first person? 1/10. And if I have 10 people, what's the probability that the first person is the third best person? 1/10. Same probability. Okay. So, our probabilistic analysis says we're going to make knowledge of assumptions about the distribution of the inputs, and those are the people being interviewed, to determine the average case behavior over all possible inputs. And we want the expected cost based on this distribution. So we can assume that the candidates come in order. Rank is kind of the quality. So Q of I, person I has quality or rank of I. That means your index may be 1. You may be 1, but your rank may be 17. Okay? So the ordered list is rank 1, rank 2, okay, like that, over the candidate numbers 1 through n. So the list of ranks is equally likely to be any of the n factorial permutations. The ranks form a uniform random permutation. And uniform random simply means equally likely. Every permutation has equally likely chance of occurrence. That's all it means. Okay? So we want to determine the number of candidates who will be hired on average, assuming that the permutation of their ranks is uniformly distributed. Now this is just nothing. This is just basically an algorithm of randomizing the candidate selection. So I'm not going to even bother with it. It's useless. Okay. We may assume, if we're not sure that the candidates are coming in random order, we can randomize them ourselves, I mentioned, and that's it. Now we're going to analyze this problem using something called an indicator random variable, or IRV, indicator random variable. Okay, simple technique for computing the expected value of a random variable. It's a convenient method for converting between probabilities and expectations, and helpful in situations where there may be dependence. The IRV take only 2 values. So the indicator random variables are either 0 or 1. That's it. So they're binary. IRVs are 0 or 1. So let's take a look over here. So the indicator random variable for an event, or some occurrence, some event A, in this case maybe a hiring or interviewing, of a sample space is defined as the indicator random variable of an event A. So this is the IRV of event A. And the value of I of A is 0 if A does not occur, and it's 1 if the event occurs. So, we're going to say X of A is a discrete, as 0 or 1, discrete value of IRV of I sub A. So we're going to let X sub A equal to represent the indicator random variable of A. And so therefore, this E is recognized in probability as the expected value, what we expect. And what we're looking for is really the expected value of the number of people we hire. We don't know how many we're actually going to hire. We're saying, what do we expect, giving our assumptions of equal likelihood. So therefore, the expected value of X sub A, the expected value of whether or not we're going to hire this person, is what happens with this over a large sample. So sometimes I of A is 0, and sometimes I of A is not 0, since it's 1. So the expected value of X of A is what is the value over a long period of time. So for example, if we find out that we hire person number 2, and then we don't hire person number 2 another time, and we hire person number 2, and we don't hire person number 2, and we don't hire person number 2, then we found out that in the sequences, we hire person 2 40% of the time. Sometimes it's 1, sometimes it's 0. But on average, it's going to be the expected value, so it's going to be 0.4. What does that mean? That means that 40% of the time, we're going to hire person number 2. You understand what I'm saying? So therefore, the expected value of this event occurring is equal to the probability of this event occurring. So expected value, okay, is simply going to equal to the probability of the event. Therefore, the expected value of x of a, since expected value of x of a is representing the IRB of a, is the expected value of the IRB of a, is going to be 1, which is the I of a at 1, times the probability of a, plus 0 times the probability of, what is this? Not a. Not a. What's not a? It's the negation of a. If a is an event, not a is that event does not happen. Okay? So, 1 times the probability of a plus 0 times the probability of not a. Well, since 0 times the probability of not a is 0, then expected value of x of a is just probability of a. So, for our IRBs, xi is the IRB, indicated random variable, the candidate I is higher. So I, the candidate I is higher, we're going to let that be represented by x of I. And so x of I will be equal to 1 if the candidate is higher, and it will be equal to 0 if the candidate is not higher. So therefore, if you took all of the x values from 1 to n, and you sum them, you will get x. And x is the summation of all of the people you actually hired. So we need to find out the probability the candidate I is higher. So let's do a little bit of thinking of how we can do this. Assuming that every person can occur with equal probability anywhere, let's look at the probability the candidate I is higher. Candidate I comes I in the sequence, right? I'm hating this lawnmower here. Candidate I is hired only if candidate I is better than the candidates from position 1 to I minus 1. Does that make sense? We only hire position I if position I is better than anything from 1 to I minus 1. Suppose that we hired somebody who was better than I in position 1 to I minus 1. If that happened, then we wouldn't hire position I, because position I is not as good as somebody we already hired. So we must have position I be the best out of all the previous people. And the previous people from I are 1 to I minus 1. By assumption, the candidates are going to arrive in random order. So candidates 1, 2, 3, 4, all the way through I also must arrive in random order. And each of the I candidates has an equal chance of being the best so far. So the probability that candidate I is the best so far is 1 over 1. Let's think about that. Probability that candidate I is the best so far is 1 over I. What's the probability that the first candidate is the best so far? 1 over 1. Certainty. What's the probability that candidate 2 is the best so far? 1 over 2. What's the probability that candidate 3 is the best so far? 1/3. And if we have 10 candidates, what's the probability that candidate 10 is the best so far? 1 out of 10. So the probability that candidate 8 is the best so far is 1 over 8, since that candidate must be the best of the first 8 candidates. They must be better than the first 1 through 7. With the candidates randomized, the probability is equally likely out of 8, or 1 over 8. So what we need to do is we need to compute the expected value of x. Expected value of x is the expected value of how many candidates we actually are going to hire. Remember, the expected value of x is nothing more than the summation of x of I over n, is the average. Expected value is the average, except it's not the average because the probability is not the same. Averages are computed when we expect the probability to stay the same, but it's not the same. If you're coming in, if there are 10 candidates to be hired, and you're coming in position 8, your chances of being hired are less than the person that came before you, and the person that came before that, and the person that came before that. And actually, if you're coming last out of 10 to get interviewed, your probability of getting hired is the lowest of all of them. So even though we're assuming equally likely positioning, with that assumption, the order in which you are interviewed changes your likelihood of being hired. Your likelihood of being hired is decreasing the later you come in the interviewing sequence. So the expected value of how many we hire, that's the summation of all the x's, is the summation, the expected value of the summation of all x's, because the summation of all x of i's is x. So what we have is the summation of expected value of x of I, or the expected value of x of I is 1 over I. So therefore what we have to do is we have to sum from 1 to n of 1 over I. How does that work? Well, when I is equal to 1, we will add 1 to the sum. When I is equal to 2, we'll add 1/2 to the sum. When I is equal to 3, we'll add 1/3 to the sum. How does that give us the expected value of x? What are we doing?
Taking the average probability.
No. We're actually summing the probabilities. Right? Because if you look at this summation, this is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, right? What's the probability the first person gets hired? Second person. Third person. Next person, 1 over 4, 1 over 5, 1 over 6, etc., etc., etc. So we're actually summing the probabilities to get the expected value. Because on average, you're always going to hire the first person. So you have to add it to the sum. On average, you'll hire the second person half the time. So instead of cutting it to 1, I'm cutting it to 1/2. Because 50% of the time I'll hire them, 50% I won't hire them. So on average, I'll hire half a person. That's the expected value. The expectation of being hired in the second position is 1 over 2. And so when I add all these together, that's what I'm going to get. Now, does anybody recognize this particular sequence? What does the sequence sum to? It's not a geometric series, because there's no ratio. It's actually a harmonic series. We talked about harmonic series too, right? And so we don't have a closed form for this. If it was a geometric series, we'd have a closed form for that. A minus A times R to the n over 1 minus R. Plug in the values, you're done. But here, we don't have a closed form. So how do we approximate it? How do we approximate the upper bound and the lower bound for this particular harmonic sequence? Integrals. We can do it by looking at the integral of 1 over x dx. Does anybody remember still what is the integral of 1 over x dx? Natural log. Yes, natural log. Very good. So, and you can see it here. So I'll show you how we're using it. Now remember, what kind of series is this? This series is strictly decreasing. 1, 1/2, 1/3, 1/4, so it's getting smaller. Since it's getting smaller, we'll start the lower bound right at the beginning, and we'll go one past the discrete end to make the intervals the same width. So, so it's decreased. I said it the wrong way. So because it's decreasing, we can't start it right there. We have to go one backward. Because it's decreasing already. So if you go from 1 to 2, you're going to, by the time you get the continuous is going to be less than, by the time we get to 2, than the 1 which stays flat until 2. So we have to go backward. So our summation, would you agree that this is equal to the same as this? I just pulled out a term, right? I just pulled out the first term when I is equal to 1. When I is equal to 1, you get 1. And then I started at 2. Why did I do that? I did it because if I have to use an integral here, I have to back the integral to what value? 0. And 1 over 0 is undefined. That makes what we call an improper integral. We don't want to mess around with that right now. So we're going to simply make it easier for ourselves. We're going to pull that 1 out, start with 2, and take the 1 here. So now we'll use an upper bound of the integral. It's going to go from 2 to n. 1 over I. And we'll use the integral, we'll back the integral to 1 to n, which is fine for us. And on the lower bound, we'll bump it from 1 and go to regular 2, n plus 1. And what we found is that the upper bound is ln n minus ln 1, which is 0, is equal to ln n. So the upper bound is ln n. So the summation, as I goes from 1 to n of 1 over I, is natural log less than or equal to natural log of n. So what does it tell us? That is the expected value of x. Expected value of x is less than or equal to this, is equal to this, which is less than or equal to this. That tells us how many people we expect to hire. And the answer is natural log of n or less on average. So let's say we have 20 people. Let's say we had 20 people. So if we were going to hire 20 people, we're going to go for 4 weeks straight. Do this. Then we take 20. If I take the natural log of 20, I will get 3. So if 20 people, I'm going to hire on average 3. So is that a bad, that's pretty good in terms of not having a very high hiring cost. That means I'm only really going to hire about 3 times. I'll interview 20 people. Okay, what kind of questions could I ask you from this? Okay. Suppose that I'm going to interview 5 people, Monday, Tuesday, Wednesday, Thursday, Friday. And the people are coming in random order. How many sequences of the people, in how many sequences will I hire the last person?
1.
Nope. In how many sequences will I hire the last person out of 5 candidates?
4 factorial. 24. 3 factorial.
So the answer is correct, is going to be 24 or 4 factorial. And the reason for that is basically, look at it this way. If I'm going to hire the last person, that means the best person must come at the end. The best person must come at the end. So there are going to be 5 slots. So we have 1, 2, 3, 4, 5. So this is going to be rank 1. Now, how many other candidates are coming before me? Do I care what order they come in? It doesn't matter. How many different people? 4. So therefore, these can be put into 4 factorial orders, but all the orders have to end with rank 1. So what's the probability that happens? Well, the probability that's going to happen is going to be 4 factorial divided by 5 factorial. Simplify it. 5 factorial is just 5 times 4 factorial, so the probability is what? 1 over 5. Simplifies very nicely, actually, right? Now let's think about if we can figure out what's the probability of hiring in the 4th position. So we want to hire in the 4th position. So we have 1, 2, 3, 4. So we want to hire in this position. How many sequences are going to be in this position? You're too fast. You're too fast. Let's think. Let's think for a second. Let's break it down. So So this person, we're gonna hire this person. This person could be the best. Right? Could they be the second best? Yes. For example, 1, 2, 3, 4, 5. We will hire them. Rank 1, rank 2, rank 3, rank 4, rank 5. We'll hire them, right? So let's think about this person being position 4. Think about the people that have to come before this position. Could 5 be in that position? Why? Because if we have 5, they're not going to get hired. Okay. They gave me 4 because I'm 4. Could they be 3, 2, or 1? Doesn't matter the order. So therefore, how many sequences are in the first 3 positions? There's going to be 3 factorial positions, right? Which is equal to 6. So that means that what's in this position? We don't really care, but it's going to be position. It's going to be top person. Okay, now, does that mean that 6, now you understand this has to be 5, right? This is rank 5, rank 4, this is rank 5. So how many permutations here? Well, 6, right? I'm just saying 6 right here. So is the probability 6 out of 120? Well, this is position, so this is what happens here. So for example, what was the question again? What's the probability of what? Hiring the 4th person. Let me ask you this. So this is the case for rank 4. How about rank 3, rank 2, or 1? Let's do rank 3. Will we ever hire rank 3 in position 4? Why? Let's say if 5 is here, forget about it. So put 5 here. 5 is not here, what's here? 4 is going to be here, so we're not going to hire. Okay, so we'll never hire rank 3 in the 4th position. Will we ever, so rank 3, will we ever hire rank 2 in this position? Or rank 2? No. How about rank 1? No. So basically, we will never hire rank 1, rank 2, rank 3 in position number 4. Is that correct? Could we ever hire rank 5, top rank, in the 4th position? Well, first of all, so now let's think about how that can happen. So basically, it actually doesn't matter who comes before rank 5, because rank 5 is going to get hired. So the question is, how many ways can that happen? So